Okay. Another application of differential equations are in the field of electrical circuits. So in this section, we talk about simple direct current electrical circuits. And this simple electrical circuit can have these kind of things in the circuit. First, a voltage source. By a voltage source, I mean like a battery. Okay, so let's say the voltage that we get from the voltage source as E. Okay, capital E. Now, another thing that you can have in your circuit is a resistor. Resistor is a device where the current goes through the resistor, but then it has a resistance to flow of the electrical charge. Now, by Ohm's law, we can say the voltage drop around the resistor is E sub R, and Ohm says the voltage drop is proportional to the current. Let's represent current by I, and to get rid of the proportionality, we can add a proportionality constant which we call R. R is the resistance and is measured by ohms, and this is the Ohm's law. Okay, another device that you can have in your electrical circuit is an inductor. Inductor, you might have seen, it's a coil of wire. What's happening in an inductor is very interesting. Okay, so I suggest you to Google and read it a little bit more, because that's not the concern of this section. But you have this coil of wire and it creates a magnetic field opposed to the electric charge. So, and it stores this magnetic field. Now, the voltage drop around the inductor is modeled by, let's say, E sub L, and it is proportional to the rate of change of current. So the rate of change of current is di over dt. I is the current, and now we add a proportionality condition constant L, which we say the inductance, which is measured by Henry. Okay. And the other device that you can have is a capacitor. Capacitor stores the electrical charge, and the voltage drop around the capacitor is E sub C is Q over C, where Q is the charge, C is the capacitance, and capacitance is measured by Faraday, and charge is measured by Coulomb. Okay, so we have all these voltage drops in the circuit, and by Kirchhoff's law, Kirchhoff's second law says the voltage drops around a loop, sum of the voltage drops should be zero. Okay, so in the source you have voltage drop E, and in the resistor you have E sub R drop, and in the capacitance E sub C, and in the inductance E sub L. So sum of these all drops should be zero. Okay, so E sub R plus E sub L plus E sub C minus E. Now, even though it's sum, we have minus E because that's the voltage source, right? So that's where the voltage coming from. So that's not a drop. So here we have it as minus E is equal to 0. From here we can get E is actually E sub R, E sub L plus E sub C. Now E sub R is by Ohm's law. We know it's R times I, right? Yes, I forgot all these laws. So R times I. E sub L is for the inductance. It's L times rate of change of current. E sub C is Q over C. Now this everything is equal to E. And in the note, I have explained how to derive a second order, higher order differential equation out of this situation. So actually you should read it, but it will come in future sections. When we move on to the higher order differential equations. Okay, so I suggest you to read it. But from out of this model, let's say we don't have a capacitor. So if we don't have a capacitor, we don't have this Q over C term, and then we get a first order differential equation. So the differential equation is L times di over dt, rate of change of current, plus R times I is equal to E. So this is the equation for a simple circuit where you don't have a capacitor. Okay, all right. So now my goal in this video is to learn a method how to solve this differential equation. So this is a first order linear differential equation. We can write it in the standard form by dividing by L, right? So di over dt, if you divide by L, it will be Ri over L is equal to E over L. Now let's use the integrating factor method to solve this. So what we can do is we can find the integrating factor. The P here is R over L. So the integrating factor is e to the integral of R over L with respect to t, which is e to the RT over L if you integrate with respect to simple t. Now you take the standard form, what you do is you multiply by integrating factor, right? So e to the RT over L, Ti over dt, plus e to the RT over L, Ri over L, ERT over L times E over L. Now we can rewrite this left hand side by shrinking it to the derivative with respect to t of integrating factor times the dependent variable I. Okay, and the right hand side stays the same. And you know what we do after this is that we integrate with respect to t, right? Both sides. So now if you integrate, the left hand side will turn out integrating factor times I, and the right hand side is E over L is a constant, so let's take it out. So if you integrate e to the RT over L, so if you integrate e to the 2x, what you get is e to the 2x over 2. So you have to divide by the constant here, right? So constant here in front of t is R over L, so we have to divide by R over L. Now division by R over L is same as the reciprocal multiplication. The reciprocal is L over R, e to the RT over L, plus C is an arbitrary constant. Okay, so L cancel out, we get our solution ERT over Li is equal to E over R e to the RT over L plus C. Okay, now let's divide by e to the RT over L, which we get I. This will cancel out when we divide E over R plus C over e to the RT over L, which we can write, we can take into the numerator by taking the negative power. So this is the solution for the differential equation. Okay, so current at time t is given by this formula, and you should not memorize this formula. You should be able to derive it using the integral factor method. Okay, so let's analyze this differential equation and solution in the next video. Okay, thank you.